Hello and welcome to the lesson on separable differential equations. So we have talked about differential equations a little bit in the course, but let's do a recap of some of the terminology. So a differential equation, or a DE differential equation, is an equation which relates an unknown function and some of its derivatives. So this word unknown, that is very important. It is the function that is unknown in a differential equation. The order of a differential equation is the highest derivative present in the equation. And if the unknown is a function, then a function is what you get if you solve the differential equation. So a function is called a solution to a differential equation if it and its derivative satisfy the equation. And then the general solution to a differential equation includes all other solutions and typically includes a number of arbitrary constants. They are constants of integration. So in Calculus 1, if you saw differential equations in Calculus 1, you may have been given the solution. You may have been given a function and the differential equation and asked to check. You have been asked to check that the function was indeed a solution. And so what we are going to do in Calculus 2, however, is we're going to go a little bit further than that. We're going to do an example. We'll do an example of this type where you are given a function and all you need to do is check. But we are going to go a little bit further. We are going to learn a technique to actually solve only one type of differential equation, and there are many types of differential equations, and there are many techniques to solve them here. In fact, you can take an entire course, or more than one entire course, on how to solve differential equations. And so we are really just going to scratch the surface here in how to solve a differential equation. So we're going to go ahead and start with this kind of example from Cal 1, where we are just going to check that the function given is a solution to the equation that's given. And then we're going to go ahead and learn a new technique for solving them. So the first example, and you may have seen this in Calculus 1, show that y of t, which is equal to a cos of omega, this is the Greek letter omega, looks like a W, but it is actually omega t plus delta, the Greek letter delta, where a, omega, and delta are constants. This is a solution to the second order differential equation, and it's second order. Why? Because the highest derivative present is the second derivative. So the second order differential equation, y double prime plus omega squared y is equal to 0. This is a rather famous equation. It's called the simple harmonic motion equation. So we want to check that this function here is in fact a solution to this equation. So what do we need to do? Well, we have the function y. We don't have its second derivative, so we need to compute it, and then we need to plug them in and see that the equation is satisfied, or that we do get 0. So to calculate the second derivative, first we need the first derivative. So the derivative of the cos is the sign, the negative sign, in fact. And with the chain rule, we get the constant omega out the front. Second derivative, so is the derivative of the first derivative. The derivative of sine is cos. The negative stays in place, and the chain rule gives us another copy of omega. So we need to plug into the differential equation and show that it is satisfied. In other words, show that we get 0. So we plug in the second derivative, here it is, minus omega squared a cos of omega to t plus delta, plus omega squared times y, so omega squared times, here's our original y, a cos of omega t plus delta, and you should see quite easily that those things cancel out, and so we do in fact get 0. So we have just verified that the function given is a solution to this simple harmonic motion equation. Nothing there was above a Cal 1 level, right? You are just differentiating and plugging in. A initial value problem. So we're going to go ahead and learn some Cal 2 stuff. Now we've talked about initial value problems, or IVPs, earlier in the course as well. It is a differential equation paired with enough conditions to solve for any of the arbitrary constants. So we've done an example very similar to this in the past, so let's refresh our memories on how we solved this kind of IVP. So here's an example. Let us find a function, an unknown function, so y is equal to f of x, given that y double prime is equal to 6. So this is a very rudimentary differential equation, and it's an equation which involves the second derivative of a unknown function f, right? So this is actually, although we didn't call it a DE at the time, this is a differential equation. And we're given more information. We're given that y is equal to 7x minus 5 is the tangent line of the function at x equals 1. So this is sort of extra information, extra conditions that should allow us to solve for any constants of integration that we will get here. So how would we have gone to solve this? Well, the first thing that we would have done is to decipher the extra information that we're given. And if y is 7x minus 5 is the tangent line at x equals 1, well, we know two things. The slope of the tangent line is sitting right there, and that slope is given by the derivative. So we know that f prime at x equals 1 must be 7, the slope of the tangent line. Also, the function f must go through the same point, right? A function and its tangent line share the point of tangency. And if that is when x is equal to 1, then to find the y-coordinate, well, we can't plug it into the function because f is unknown, but we can plug it into the tangent line since it is a shared point. So if we plug 1 into the tangent line, we see that the y-coordinate, f of 1, must be 2. F of 1 must be 2. So those are two extra conditions. We know the derivative at 1 must give 7. We know that the function at 1 must give 2. Those are our conditions. And then we have the original information, which we are now reframing as a differential equation. So how did we go ahead and solve this before? It was very easy. We just anti-differentiated. We integrated. We just integrated because if this is the second derivative, we know that the first derivative is an antiderivative of the second derivative, and so we anti-differentiated. So y prime is an antiderivative of y double prime. Y double prime was 6x, so we anti-differentiate this. We get 3x squared plus c. C is an arbitrary constant of integration, so what did we do? We plugged in one of the conditions, namely this one, to solve for c. So y prime of 1 equals 7. Plugging in 1, you get 3 times 1 squared plus c. If that has to equal 7, then c is 4. So we have now the first derivative. We don't want just the first derivative, we want the original function, so we're going to go back up one more step. Integrating again, the original function y is as an antiderivative of the first derivative, and so anti-differentiating again, we get this with another arbitrary constant of integration, d. Luckily, we have one more condition. We have one more condition to plug in, and if we plug in that y of 1 is equal to 2, plugging that in as we do right here, that's enough to solve that d is equal to minus 3. So we have here the original function. That was our unknown function that is now solved for. That was our unknown. Now, this, let me just make a little comment here. This kind of differential equation is the easiest form to solve, and that is when one of the derivatives is just given or isolated, right? We were given, actually here, we were given d squared y dx squared was 6x. We were given the second derivative, but the first derivative could just be given. And what do you do to solve? Well, you just integrate. If you're given the derivative, you just integrate. right? So that we did earlier in semester, that is not new. What is going to be new is this. What if this form is not given? What if the equation that you're given has x's and y's mixed up? That is the new little wrinkle that we are going to add in here to solving differential equations. And so a separable differential equation, specifically a first order one, is a differential equation which can be factored. So I said x's and y's are mixed up. Yes, potentially, but mixed up not too badly. Mixed up so that they can still be factored and put in the form where dy dx is a function of x times a function of y. In other words, the x's and the y's can be separated into two different factors. If we have this condition, this is how we're going to go ahead and solve it. For all values where f of y is non-zero, we can write h of y is 1 over f of y. So why would we want to do that? Well, we would want to do that here so that we push f of y down into the denominator as 1 over f of y. And if 1 over f of y is equal to h of y, we can just rewrite this factor as a quotient, g of x over h of y. If we rewrite that in differential form, it looks like we are just multiplying up the h and multiplying up the dx. That's not exactly what's happening, but that serves just as well for a good memory aid as to what you are going to do. So this is differential form. We have h of y dy is g of x dx. This now, if we integrate on both sides, then this is now something that we know how to deal with. In fact, it's two somethings that we know how to deal with. We know how to integrate in, well, many techniques that we've learned this semester. So we are going to get constants of integration, constants with an s, because you have integrals on both sides. So in theory, you are going to have one constant of integration on each side, but then they can just be combined, right? If I have a c1 on this side and a c2 on this side, I can bring this guy over here and have c2 minus c1 and just call it some constant c. So they can be combined into a single constant. So even though there is two antiderivatives, you only need, in this separable case, a single constant of integration, which actually you can place on either side as you see fit, as is appropriate to the question. And if this differential equation happens to be part of an initial value problem, if you have extra information, that constant can then actually be solved for as well. And lastly, once you have integrated and you have expressions on the left, which is in terms of y, and on the right, which is in terms of x, if the expression on the right allows you to do so, we can actually isolate y and get the answer that we are looking for, that y is f of x, right? Up here we said that dy dx was the derivative, and so we are looking for this function f of x, y as a function of x as our final answer. Now, that is a big if. That is a big if. So sometimes you'll be able to isolate for y, sometimes you won't, and we're going to see one of each kind of example. So let's look down here. Two examples. Number one, solve the following IVPs. The first one, we have dy dx is, oh, look at that, x and y are mixed up together on one side, and we've given the precision that both of those are positive. We are also given y of 4 equals 9, which is telling us that at x is equal to 4, y is equal to 9. In other words, the function goes through the graph at 4, 9. The function graph goes through the point 4, 9, if I say that properly. So how do we solve this? We are looking for the function y. We want to know y is what? So we are going to separate this, like the name says, separable differential equations. if x and y are both positive, I can split that root into two roots. So dy dx is root x times root y. Divide on both sides and put in differential form, which looks like we're sending the root y down and we're sending the dx up. That is an absolutely okay thing to use as a memory aid here, and then we slap an integral up. We're going to integrate on both sides. These are two integrals that we know how to do. In fact, they're both power rules. They're both power rules, y to the minus 1/2 and x to the 1/2. Integrating both, right? And that is not true. There's a little mistake there. So y to the 1/2 over 1/2, which is like multiplying by 2. X to the 3/2 over 3/2, which is like multiplying by 2/3, plus c. Now we have to go here and use these conditions. This condition here that when x is 4, y is 9. And so let me add in what we are missing here. So we have 2 times 9 to the 1/2 is 2/3 times 4 to the 3/2. So we're going to have 2 times 3 is 2/3 times 8. So this is going to give me, let me do a little computation here. We're going to have 6 is equal to 16 over 3 plus c, which means that 18 over 3 is 16 over 3 plus c, or c is 2/3, not minus 5. It's a good job. It's a good job that I can see this the second time round, because I clearly didn't see it the first time round as I did this through. So c is equal to 2/3, and we have this equation. So if this was our, no it isn't. No, it isn't. We had 2y is equal to 2/3 x plus 2/3. So now we want to solve for y. We're going to divide both sides by 2. This is all messy. Let's get rid of that. So y to the 1/2 is divide both sides by 2 is 1/3 x to the 3/2 plus 1/3. And now I can square both sides. Y is 1/3 x to the 3/2 plus 1/3 all squared. And so there it is. We have solved for our unknown function. We have solved for our unknown function. Second example, let's hope I don't catch another mistake in this one. So second example, dy dx is y times cos x all over 2y squared plus 1. So they are all mixed up again, the x's and the y's. Y of pi over 2 is equal to e. That tells me that when x is pi over 2, y is e. So we're going to go here and solve. We're going to do here by separating. This is y over 2y squared plus 1 times the cos of x. So if I bring this over to the other side of the equation, I get 2y squared plus 1 over y times dy is cos of x dx. Now, integrating on both sides, this here we can simplify by splitting the numerator. So I get 2y plus 1 over y dy is equal to, and so we're integrating both sides, the integral of cos x dx. Integrals that are very easy to evaluate. So y squared plus ln of the absolute value of y on the left. Integral of cos is sine plus c. Again, we need just one constant of integration. Now we're going to use this point here that at x is equal to pi over 2, y is equal to e. So we plug that in. We plug that in first for the x and for the y value. And I should make a point that before you solve, actually in this case it is going to be impossible to solve for y, but even if it were, solving for c, plugging in the conditions is better to do before solving for y, before isolating. Right? So that is better to do most typically to solve for c, to plug in those constants, those conditions first before you try isolating. That is my recommendation to you. And so here the sine of pi over 2 is 1. The ln of e is 1, so those things cancel out. And we get c is equal to e squared. C is equal to e squared. So plugging back in for the c value, we get y squared plus ln y is equal to sine x plus e squared. And it is not possible to isolate the y. So what do? Nothing. You just leave it there as the same way that you would have dealt with implicit functions in your calculus 1. I mean, we're not going to differentiate them or anything here, but this is kind of the implicit solution. There is no way of isolating y to make an explicit solution, so you just leave it there.